Hello, today we're talking about section 6.5, estimating area with trapezoids. So this is going to be very similar to yesterday. Yesterday we estimated area using rectangles. Now we're just going to do the same thing with trapezoids. There's going to be a few different twists and turns on it, but nothing too bad. So first off, got to remember how to find the area of a trapezoid. Area of a trapezoid is 1/2 of the height of the trapezoid times base 1 plus base 2. In this particular case, the trapezoid is standing vertically, so the height is actually right there, because the height of a trapezoid is the distance between the two parallel bases. So this trapezoid would have an area of 1/2 times 2 times the sum of the bases, 5 plus 3. Let's see, that'll be 8. All right, let's actually get to it with problem. Oh, there's a notation note. You are going to see this notation today because you might have noticed we jumped way ahead to section 6.5. The reason we did that jump is because 6.1 is estimating area, and then so is 6.5. So it kind of makes sense to do those sections together. This notation here is a notation called an integral. We are going to learn a lot about that one. In fact, that's the next major concept of calculus. The first one had to do with derivatives, dy dx. We learned all about that. Now we're learning about something called an integral. For now, it's just all you need to know for that thing is that when you see that sign, that's talking about the area under a curve between those two x values. So if I was taking the integral from 1 to 3 of x squared with this little dx after that, that just means that over here, I've got the graph of x squared, and I'm looking for the area starting at 1 and ending at 3. So I'm looking for the area under that curve right here. This integral is talking about exact area. At this point, we don't know how to give exact area, but we can estimate that area. We can estimate it with rectangles, which we did in 6.1, or as we're going to do today, with trapezoids. So we're going to start right away. So let's estimate the area using trapezoids. You've probably noticed already that trapezoids have a big advantage over rectangles. If I were to estimate this with, say, LRAM would use these rectangles, which would be continually an underestimate, right? I'm not going to be counting that area or that area, that area. If I estimated with our LRAM, I would be too low. If I estimated with RAM, I'd be too high. But trapezoids do a pretty good job. Like if I drew a trapezoid in here, it's going to be a pretty close estimate of that curve. It's not going to be exact because this is a curve, and you can see, like, if I zoom in, there's going to be just a little bit of a miss there, but it's going to be pretty darn close. So trapezoids are a really nice estimate. All right, so how do you do it? Well, you find the height of each of those trapezoids. This particular problem is starting at x equals 1, going all the way to x equals 3. So 2 must be there. So that must be 1.5 and 2.5. So it looks like all my rectangles have a height of 1/2. And then I just got to know the bases. So to find these, well, that's just the height of that line. That would be f of 1. So plug 1 into your x squared. 1 times 1, that's 1. And then I could find that. That'd be f of 1.5. Plug 1.5 into the x squared, etc. So let's actually do this. I think the way I'm going to do it is I'm going to find these heights first. I'm going to use my calculator. I'm going to find how tall each of these heights are by just, again, plugging those values into x squared. All right, so my first trapezoid is going to have an area of 1/2 times the height, which is this distance, 1/2. Base 1 is a height of 1 plus 2.25. That's my first trapezoid plus the second trapezoid. 1/2 times it's got a height of 1/2. And then the bases are 2.25 and 4. And you just keep going. There it is. I would just plug all those into my calculator. I get 8.75. There it is. All right. There is a way I can use the trapezoid sums to compute it faster. We're going to talk about this one really quick. If I found the sum of these areas, I'm just using y0, y1, y sub 2. I'm just using those for my heights. If I wanted to sum those areas, I could add all those trapezoids up. It would look like this. 1, 2, 3, 4, 5 trapezoids added together. But you'll notice for these 5 trapezoids, since the height of each of these trapezoids was the same, my formula always started with a 1/2 h, 1/2 h, 1/2 h. If your trapezoids are all evenly dispersed like that, I could factor that 1/2 h out and actually come up with what's known as a trapezoid formula for computing an area faster. If you factored the 1/2 h out, it would look like this. There'd be a single y sub 0, but you'll notice the y sub 1s happen twice, the y sub 2s happen twice, and so do the y sub 3s, all the way up to the last one. So it'd be y sub 0 plus 2 y sub 1s, 2 y sub 2s, etc., all the way up to a single y sub 5. And that could be a single computation I could do to find the area of those 5 trapezoids instead of doing 5 separate ones. We're going to try that with this same problem. So here's that formula in general. It's h over 2, or 1/2 h if you prefer, times the sum of all the heights, where the first height and the last height are by themselves, but everything in the middle is times 2. All right. So we had already computed these heights before, and all of these bases were 1/2. So if I wanted to do the same area of x squared with trapezoids, I could use this formula. In this case, it's h over 2. So 1/2 over 2. Or if you prefer, 1/2 times 1/2, right? Because some people prefer this, some people prefer that as 1/2 h. That's fine. 1/2 times 1/2, same thing. Times the first one is 1, plus 2 times the second one, etc., all the way up to the last one, but I only have one of those, not the 2. And then I could just put that entire thing into my calculator. If I did that, I guarantee it should be the same number we had before, 8.75. So just a different way to calculate the trapezoids by using that trapezoid sum right there. All right, one last thing. I've got the trapezoid sum here. So I've got a curve here, and I don't know that I can really see the trapezoids, but yeah, I can. I've estimated the trapezoids in red right here. So there's a trapezoid, there's a trapezoid. I've just kind of outlined the trapezoids in red. So I've got a trapezoid sum, but ignoring that red, I've also got the RRAM and LRAM pictures in there. One of those is purple. So I got a bunch of purple rectangles. I also have a bunch of pink rectangles. The pink ones are overlapped by the purple. They go all the way down to the bottom. So that would be the pink rectangle. Really quickly, you should see if you can identify which color rectangle is LRAM and which color rectangle is RRAM, because you should be able to tell the difference between the two. All right, LRAM again has the left-hand corner hitting the curve. Since this is my curve right here, the left-hand corners of the purple rectangles are hitting that curve. So the purple rectangles are LRAM. RRAM, of course, has the right-hand corners hitting the curve. They are the pink ones because there's a right-hand corner, and those pink ones are hitting the curve with the right-hand corners. The reason I'm superimposing this, though, is if you look at the LRAM is continually underestimating my true area under the curve. Right? They're always those ones are always too low in this particular curve. RRAM is currently is absolutely overestimating, but the trapezoid splits that difference right in half. You notice how the trapezoids take that error, and that error is like a rectangle between the two, and the trapezoids connect those two corners, which means the trapezoid sum is exactly halfway between the LRAM and the RRAM approximation. Well, if it's exactly halfway between LRAM and RRAM, it's actually equal to the average of LRAM and RRAM. So how does a trapezoid approximation compare to LRAM and RRAM? It's the average of LRAM and RRAM. That's not terribly important to know, but it just gives you another way of finding the trapezoid sum. If you happen to know the LRAM approximation and the RRAM approximation, you don't have to recalculate to find the trapezoid approximation. It's just the average of the two. All right, summary. 3 ways to estimate area of trapezoids. 1 is to just use your trapezoid formula. The advantage of that one is you should already have that formula memorized, so it's nothing new to memorize. Second way you could do it is you could use this new formula we came up with today. H over 2, or 1/2 h if you prefer, times the sum of all those heights. Again, where the middle heights are all times by 2, but the 2 edge ones are by themselves. And then the last way, which we probably wouldn't use often, but it's a good thing just to be aware of, is you could find the average values of LRAM and RRAM. There is an important note here. The trapezoid rule can make calculations faster, so that is one way to, one advantage of the trapezoid rule. However, we are not going to use trapezoid approximations frequently. That's a pretty infrequent thing. There might be one question on the AP test about the trapezoids. They're not a hugely, it's not one that shows up a lot. It does show up, I've seen it before. But the thing is, as far as memorization, like you could spend time memorizing that. It's an easy thing to memorize, and then you got it and makes your calculations quicker. But if you're not going to spend time memorizing it, then you might be better off doing that one because you already have that formula memorized. All right. My advice is to not memorize it because it's just so easy to forget. But if you think it looks, nice and quick, maybe give it a shot. It's up to you. All right. Last one. Here's a table of values. I mentioned this in 6.1, but just as a reminder, if they give you a table of values, this is no different than if they give you f of x. F of x is just the heights at all those points. So at x equals 0, my function has a height of 10. At x equals 1, my function has a height of 12. If I were to estimate the area using this table, I would probably use that second method because it's really set up well for it right now, right? I can look at here, I say, all right, the difference between my x values is always 1. So that means my height is 1 of each of those trapezoids. So if I was to estimate this area, it'd be 1/2 times 1 plus, not plus, times the sum of all those heights, starting with the first one, doubling all the middle ones, and ending with the last one. Starting with the first one of 10, plus 2 times 12, 2 times 15, etc. Till you get to the very last one, and just a 5 for the last one. That's going to do the trapezoids. As always, if the table is throwing you off and it's really like, I'm not sure where these numbers are coming from on the table, you could always sketch it. Basically, I've got some curve that looks like this, making up that curve again, but I know these different heights, right? So then you can make your trapezoids. So if you need to actually do a sketch to make your trapezoids, you can. But if you don't need to, don't waste your time with it. All right. I feel I need to finish this. This actually ends up adding to 51.5. That's an estimation of the area under the curve. All right, I'm done. The assignment is just 3 problems, 3A, 6A, and 7. I'll see you later.